we are looking at the third problem from 2019 Combined Mathematics LO past paper. This is the one with the complex numbers. So let's get started by reading the question. This one says, sketch in an Argand diagram the locus of the points that represent the complex numbers z satisfying the z satisfying the argument of z minus this complex number has an angle 3 pi over 4, negative 3 pi over 4. So what does that mean is, as you should know, if you have two complex numbers, z minus w, and if you are finding the argument, this means the angle considered in this way. If you have the w in the Argand diagram at some point, then the angle measured from w to z, wherever that is. For example, if my z or z complex number is lying here, then that angle from here to this line is the argument between the two um, complex numbers. So in this problem, we are looking for all the complex numbers that you can put as z or z that is making an angle from this complex number here to be negative 3 pi over 4. Looking at this, if I rewrite this formula by taking the negative out, that's going to leave me with 2 plus 2i, and that has to be negative 3 pi over 4. Therefore, in the Argand diagram, by indicating this 2 plus 2i, which should be somewhere here with the real part 2 and the imaginary part also 2. So this is my 2 plus 2i complex number, and then all these z complex numbers should be making an angle of negative 3 pi over 4. So from this, if I have the angle negative 3 pi over 4, it's the angle that makes the line go through the origin like this. So any complex number that is a point on this line satisfy this argument formula given here. So we have therefore drawn the locus of the point that represent complex numbers satisfying this. Now we come to the second part of the problem. It says, hence or otherwise find the minimum value of the magnitude or the absolute value of this I times the z bar, which is conjugate of the complex number, plus a 1. Remember, we have to do this with this formula satisfied. We just found that formula shows the z values or the complex numbers to fall on this line. So we have to make sure this is z one of these complex numbers. In other words, this conjugate you have taken here is of a complex number you have on this line. So when it says hence, we can use this diagram we have drawn already to come up with our answer, because this line shows all these z complex numbers. You just have to take the conjugate of that and then find the magnitude of that complex number. There are two different ways that we can look at this. One is to think about the complex number properties that we know and then go from there. I will show you both methods. That's one method, and the other one is to write a complex number in its usual form that we write a plus bi form, and then use it to come up with the minimum value in a different way. So let's first start with the fact that we have as a property. If you think about, before we get started, let me just show this and then we can discuss that. If we have, say, z minus w, two complex numbers, if you are looking for the magnitude of the complex number formed by taking the difference of these two, that actually means on a diagram, Argand diagram, if we think about this diagram we drew earlier, then that is the distance between the two complex numbers we are looking for by this. So the magnitude of the difference of the two complex numbers shown here in the Argand diagram, that will be just a distance question question. So you just have to find the distance between the 2 points that show the 2 complex numbers. So I'm going to do that method first. For that, I have to write this particular absolute complex number formula in this form, where you just have the z, that's one of these complex numbers, and then minus, we have to figure out what w is in this situation. So let's use some properties of the complex numbers to get this to look like that. I start with the given. So we have I z bar plus 1, and then we can write I z bar. If you pull out the I and then write the factors left, then you can see the 1 leaves a negative I when you pull out an I. So you can verify that by multiplying it back. I times the z bar gives you the first term. I times the negative I gives you the plus 1. Now this is inside the absolute bar. Now when you have absolute bars, if it is just I times all this, you know this is equal to just the absolute or the magnitude of this part of the complex number. Because what happens when you do the magnitude, if you write your complex numbers in the form a plus bi, you know when you find the absolute value, it's going to be a squared plus b squared square root. So if I just have multiplied these with another I, if you think about multiplying this with a I, then it's going to be just ai plus b negative b. So we have negative b here in that case. Now when you do the absolute value of this particular complex number, it is still going to be a square plus b square square root. So just multiplication by I doesn't change the magnitude of the complex number. Therefore, this is just equal to that. Now notice that this equals to z plus I bar. And that is because of this. If you have z equals to a plus bi, then z bar is equal to a minus bi. So if you just have z bar minus I, that's just the imaginary part subtracted. So if you write this z in the a plus bi form, then that z bar is a minus bi. So if you just have this part, this is a minus bi with another I. So we see that if you think about the z plus I bar, that would be a plus bi plus I bar. In other words, that is a minus bi minus I. So it's the same thing that we have here. So when you have that, that is equal to this. And then we know z bar, a conjugate of a complex number magnitude is the same as the magnitude of the complex number without the conjugate. So this absolute value just can contain the conjugate of this, or without the conjugate of the original complex number here. This one is the form that I kind of want. I want to have my complex number absolute written in that form. To make that happen, all I have to do is just bring in a negative in between, which makes it negative I. Therefore, that W here is like my negative I here. Now this absolute value, well, this one is what we were trying to evaluate. Now that equals to this, and this is one of these points that you see on this line. And negative I, we can pinpoint that one in the Argand diagram. Negative I would be 1 unit down. So if I mark that on my Argand diagram, that should be somewhere here. That's negative I. So then, what is this absolute value is asking? What is the magnitude? This is asking the difference between, or the distance between, this complex number and that complex number. So that in the Argand diagram, I can see clearly in here. The distance would be the shortest distance that I am looking for here. So this is the minimum value of that. Therefore, this would be a minimum. The difference between any complex number z on this line and this particular complex number here would be when you do a perpendicular drop to the line from the negative I complex number. So finding the distance between this particular complex number negative I and this value of z, this is the z line, any complex number, but you the one that is closest to it, and now you can find the distance between these two. If I call that, well, distance d, then how do I find the value of d? We know this here makes a right angle triangle. So this hypotenuse is of unit 1 length, and the angle here or here is 45 degrees or pi over 4. Therefore, using that fact, we have a unit 1 and this angle is pi over 4. This is 1 unit here. Therefore, that d value should be just cosine pi over 4, which is 1 over root 2. And that is the minimum distance between any complex number here and that negative I. And this is equal to this. Therefore, we have just found the minimum value of this particular absolute value of the complex number. Now let me discuss another way to do this problem. For the next method, I'm going to use that usual way of writing a complex number. When z is given, we write a plus bi in place of is. This new method will fall under the otherwise method if we do it. And what we just did falls under hence because we used this diagram to come up with this answer. Right now, when you use a plus bi kind of written for z, we won't use this diagram. We don't need it. Since our z satisfy this situation, all the complex numbers should have, if we write it in a plus bi form, I should be able to write it a plus ai using both the real and the imaginary parts to be the same, because our angle is negative 3 pi over 4, giving us a pi over 4 angle here, making sure every time that a and the b values are the same. So each z value in particular, for example, if you pick the one at 1 and 1, so you see a value and the b value is always the same. So in general, I can write a plus ai for any z value that satisfies this condition. Now I want to find the minimum value of this absolute of this complex number satisfying this condition, which means my z values here can be written in that form. Then what do I get out of this if I write z to be a plus ai? Starting with the given, I have I times the conjugate of z plus 1. So replacing my z with a plus ai, the conjugate, I get just I times a minus ai plus 1, and this is ai negative ai squared, which is plus a plus 1. So you see we have the absolute of a plus 1 plus ai as the complex number inside there. And this should be equal to the square root of the square of a plus 1 plus a squared. Little simplification gives us a squared plus 2a plus 1 plus a squared, which is equal to 2a squared plus 2a. Now to proceed from here, we want to find the completing or the complete square inside the square root, which turns out to be, if I continue it up here, pulling out that 2, it's going to leave a square plus a from the first two terms. Because we are just completing the square, we just need the first two terms in order to do so. And then 2 times, in here you can write a plus 1/2 squared. There's this plus 1 out here. Now we know a squared gives us that one, then 2 times the multiplication of these two gives us a, but the square of this is an additional term that comes out of this square. So 1/2 squared is 1/4, and then multiplied by 2 is a 1/2, but that 1/2 is additional, therefore you can subtract that 1/2 from the rest of it, giving us this as our result. Now simplifying inside the square root, you end up with 2 times a plus 1/2 squared plus 1/2. So looking at this, now I see this term that involves a can only be positive because of the square, or 0, and therefore this square root, if I think about the minimum value of this square root, what do I think about the minimum value of this square root? And that square root is the same thing as this particular absolute value, which is the one that is given in the problem. We are looking for the minimum value of this quantity, and that quantity now simplified to this square root. So as long as I find the minimum value of this, I find my answer. So this square root will be minimum when the terms inside gives you the minimum possible value. Since square makes this part always positive or 0, the minimum value for this part is 0, and that happens only when a equals to negative 1/2. So when a equals to negative 1/2, this will be 0, giving us just square root of 1/2 as the minimum value possible for that term. So the minimum value possible is square root of 1/2, which is 1 over square root 2, and this is when a equals negative 1/2. So this is one way to find that minimum value. This is the same answer we got earlier. This time we had to go through completing the square by writing this as a plus ai. Please make sure you subscribe to our channel. We look forward to more problem solved like this that help you with your A-level examination. See you again in a new video.